How we doing, guys? I see Jasmina and Gabe in there as well. Jasmina's gone.
Good morning. Hello.
Hi, Gabe.
And then there were three.
Yeah, there should have been four. Jasmina went away. Don't know why. Cassidy's here. Gabe, you got a point. You're not excited about that, Gabe?
Oh, I did?
Yeah, for the guessing. You guys did really horrible at this. You're definitely not on sync with me on those questions.
Oh.
The
scavenger hunt?
the scavenger hunt, yeah.
Oh.
If you're really interested, I put my answers at the very end of that. So how we doing? Did anybody do anything foolish like study over the break?
I worked.
You did? You didn't go out to the beach?
No, I had work all weekend.
Too bad. I was in South Florida.
What?
I was in South Florida at the Intercoastal watching all the Trump boats go by.
Oh gosh, yeah. I wish I could go to the beach. I had to work, so.
Where do you work, Cassidy?
I work at like a juice and smoothie bowl place.
Okay.
Yeah, really easy job.
It gets you through.
That it does.
It gets you through. Kevin's in. Kevin got a point. No, hey, how come you guys didn't answer the question? This was an easy way to get points. I mean, the most of you guys got were 4. 4 out of 10 right. You got 4 out of 10, and the first 2 were gimmies. The first one was who was born the furthest away from Tampa, and the other one was who loves pets the most. And that was Min Bin for the first one, or Caitlin for the second. And you guys didn't even, that's halfway to getting a point for how much a point's worth. How we doing? We doing okay, guys?
Yeah. Did I get the closest?
Kevin, you got a point.
Yes.
Kevin. Ooh, that 1 point out of 1,000 is going to kill. That is going to make or break your grade.
Hell.
Okay, guys. I don't think we're going to get too many more here. I'm down to 5 of you. We're going to wait. We're going to wait and see what happens after the first test, after next Tuesday. And we're going to wait and see what Thursday's attendance is like. Exam is next Tuesday. That should be the 15th, if I'm not mistaken. Are we good? We good with that?
Yes, I have a question.
Yeah.
Okay, Kevin.
With these 3 posts we have to do, what exactly are we supposed to do? I'm like a little confused.
Kevin, just all you have to do is make a significant comment. That's all. 1-2 sentences. Okay? And
A comment on a previous post?
you can comment on a previous post. If somebody is asking a question, you can answer their question. If I post 3 homework questions a week. If you're stuck, grab those 3 questions and answer them. Okay?
Okay.
Does that answer your question, Kevin?
Yeah.
All right, Kevin, I'll ask you another question, Kevin. How much free time do you think I have?
If you're like me, you have none.
Basically, what I'm do is I look through the homework because those are the most important, and I make sure that somebody is not disseminating bad information. Okay? Then after that, I just kind of like count to see you got the 3, and then I'm done. So basically, you could recite the Gettysburg Address, and I probably wouldn't know it. All right, any other questions before we start on reactions? We went through double displacement, ionic, net ionic. Then we went through single replacement. And remember, single replacement it involves the more active species. What you do is you look at the things that are given to you. In a single replacement, you will be given an ionic compound and a neutral compound. And you got to gauge between the neutral compound and the ionic compound, which one is going to be more active. If the neutral compound is more active than the cation, it will replace it. If the neutral metal is less active than the cation, then it won't. Seem to be fairly easy. Kevin, I got you up here. I have magnesium and silver nitrate. I know that's a single replacement because I have a neutral metal and I have an ionic compound. Okay, so as soon as I pop it up here, as soon as I find it, there we go. Now we have magnesium and silver, Kevin. Which one is more active? Are you seeing the screen, Kevin? Magnesium is more active. So if I have neutral magnesium and I have silver nitrate, will I have a reaction?
No.
The more active one wants to be ionic. If I have magnesium, it's more active than silver, and I have the reaction. Magnesium plus silver nitrate. Is magnesium ionic right now?
Oh, yeah. I thought magnesium was part of the compound. That's why I said no.
No, magnesium is the neutral compound. Does it want to be ionic, Kevin?
No.
It does because it's more active. All right? The more active metal between, and you're choosing between the metal and the cation. The more active metal between magnesium and silver. And you agreed that magnesium was more active, correct?
Yeah.
Then what you have to look and you have to see, magnesium is neutral now. It's more active than silver, so it wants to be ionic. So therefore, it's going to replace the silver, and I'm going to make MgNO3 plus Ag. Does that make sense to you, Kevin?
Yeah.
All right, we're going to go for the next one. We have iron and we have copper chloride. I'm going to go back to the activity series. We have iron and we have copper. Which one is more active, Kevin?
Iron.
Iron. So iron is more active, but I have the equation. Iron metal is reacting with copper chloride. Which one is more active, iron or copper, did you say?
So the iron wants to be ionic then.
So the iron wants to be ionic. What are my two products?
Cu and FeCl2.
Yes. Here's a clue, guys. Here's something. Can somebody tell me whether iron is a type 1 or a type 2? Is iron a type 1 or a type 2 metal, guys? Somebody answer the question.
Type 2.
Type 2. So, Cassidy, when you make the product out here, as this is written right now, do you know whether you're creating FeCl3 or FeCl2?
No, because there's no charge on iron.
You don't know. So, in other words, if you get something like this in a test, that's something to call me about. I will try very strongly. If I give you a single replacement reaction, I will try very strongly to give you a type 1 metal so that you know what the products are going to be. Does that make sense to you?
Yes.
And I will check that in the test. I will check it before I hand the test out to you. If you do, if it inadvertently does, if I do put a type 2 out there, then be aware. that you can't answer the question, what I would do in that instance, choose one. And if I were you, I would choose the simpler one. I would make it going to iron +2. Make this FeCl2 plus Cu. Does that make sense to you guys?
Yes.
Good, Cassidy. Off the top of your head, do you know whether calcium is more or less active than hydrogen?
I would guess more.
Actually, it is. Good guess. You should buy a lottery ticket this week. Calcium is more active than hydrogen. So Cassidy, would you expect the calcium to replace the hydrogen?
Yes.
So in this instance, the calcium will replace the hydrogen, so you get a new ionic compound, the calcium chloride, plus, again, because this is hydrogen, hydrogen has to exist as H2. Okay?
Okay.
Gabe, you out there, Gabe?
Yeah, I'm here.
Okay, the next one down is sodium plus magnesium sulfate. Sodium and magnesium. Which one is more active, Gabe?
Sodium.
So, are you expecting a reaction?
Yes.
And what are your products, Gabe?
It's gonna be. Would it be? Oh, NaSO4 and Mg.
Yes, it would be MgS. Excuse me. It would be Na2SO4 because sodium has one charge. SO4 has a 2 charge.
Oh, yeah, -2.
And magnesium. All right, last one. Gavin, you out there, Gavin?
Hi, Captain.
It's zinc and potassium.
Mm-hmm.
Which one's more active?
The zinc is.
Look at the chart.
Or, sorry. Potassium is more active than zinc, so there's not going to be a change.
Okay, did you get that, guys? Potassium is more active than zinc. So potassium is already ionic. So the bottom reaction, there would be no reaction. We good with that? Okay. I'm assuming by the crickets that we're good. All right, we're going to go on. All right, let's see who else is out there. Gabe. And I know there's somebody. Gabe,
Yes.
how do you recognize an acid? If you have a formula, how do you know that something is an acid?
Doesn't it have like?
I don't know. It's a great answer, Gabe.
I mean, couldn't you tell by like? Yeah, probably. I don't know.
I don't know. It's a good answer. Jessica, do you know? Jessica? Jessica was out there. And she's apparently not answered. Jasmina. Jasmina,
Yes.
you out there?
Yep. Hi.
Hi, how you doing today?
I'm good. How are you?
Doing great. If you have a
Good to
chemical
hear.
formula, how do you recognize something as being an acid?
Hydrogen atoms.
It begins with hydrogen. Gabe, if it's not water and it's not hydrogen peroxide, H2O, H2O2, then if the formula begins with H, it's an acid. Okay, Gabe?
All right.
Now, Jasmine, I'm going to ask you this. How do you recognize a base?
I don't know. I guess anything without hydrogen.
Nope. Nope. Nice try. Nice try. Anybody out there?
Yeah, I guess.
Doesn't it require oxygen?
What's that?
Doesn't it require oxygen?
Requires oxygen and
Would it be a cation with
Nope.
oxygen?
nope. Anybody else out there? How do you recognize bases? All right.
Does it have a O?
Go ahead, Jessica.
Does it have a OH at the end?
OH at the end, guys. So if you have an acid, a compound that begins with hydrogen, and you have a base, something that that has an OH as the anion, these act as an acid-base reaction. It acts the same as a double replacement. So if I have something like HB reacting with COH, the first cation, the H, reacts with the second anion, the OH, and we make water, H2O. Whatever is left, the cation of the cation on the base reacts with the anion on the acid to make an ionic compound. Guys, ionic compounds are also called salts. So the product of an acid-base reaction is always going to be water. Then all you got to do is look at the cation on the base and the anion on the acid, and you make a salt from that. Ionic equation, if we break up the HB to H plus and B minus, we break up the COH to C plus and OH minus, we make H2O plus C plus and B minus. Now, Jessica, what's the same on both sides of my ionic equation here?
The B.
B minus and
The C.
C plus. So if we cancel those things out, all that is left is H plus OH minus yielding H2O. This is an easy question. The net ionic reaction of any acid-base reaction is H plus OH minus yielding water. Now, if we have a real equation like HCl and NaOH, we break the HCl, the H reacts with the OH to make water, leaving Na and Cl to make NaCl. Acid-base reactions. What are my products? We'll go with Jessica.
Yes.
What are my products here?
Oh, H2O,
And what's left?
potassium, sulfate.
H2O. As a matter of fact, I'm going to probably have two H2Os plus K2 because potassium's a +1 charge. Sulfate is a -2. K2SO4. Okay, are we good with that? So in
Yes.
this case, I have two H2Os plus 2 no, sorry. This is not a 2. This is going to be K2SO4. And I'm going to need to put a 2 there. Okay? Are we good, guys? Does this make sense to you?
Yes.
Kevin, yeah, good. Kevin, you there, Kevin?
I am here.
So, what did I say? Does this begin with an H?
Yeah.
Does this begin with a, or does this end with an OH?
Yep.
So, do I have a acid-base reaction here?
Yes.
What are the products of an acid-base reaction?
What is that? 3H2O plus
What's left? You took care of the H's and the OH's. What is left?
3. So
Nope.
3NaPO4.
Nope.
Oh, just NaPO4.
Just put the products together. NaPO4. Now, Kevin, do you know the charge on that Na?
No, I think +1.
+1. How about a PO4?
Isn't that like -2?
Nope. Look over here, Kevin. Sometimes the question will give you the answer. Okay? What's the charge on H?
3.
Nope.
Oh, what's the charge on H? Oh, I'm not sure.
See my finger?
1.
1. Okay. So how many of the H's are there?
3 of them.
So what's the total positive charge?
3.
What's the total negative charge have to be?
3. Okay.
So what subscript goes under sodium?
3.
3. So balancing it, balance the sodiums, I get 3 of those. Balance the H2Os, I get 3 of those. And literally, I am now balanced. Okay?
Okay.
All right, Gavin. You there, Gavin?
Yes, Captain.
Okay, Gavin. Do I have an acid? Last one. Do I have an acid?
Yes.
Do I have a base?
No.
So is this last reaction an acid-base reaction?
No, sir.
It is what kind of reaction? Okay, Gavin. Let me ask you a couple.
Is it going to be also a double replacement?
It's going to be a double replacement. You have to remember, guys, that acids are ionic compounds, bases are ionic compounds. So if I have an acid mixed with another ionic compound, it is not an acid-base reaction. It is a double replacement reaction. So in this reaction, I would have the H hooked up with the Cl to have HCl, and I would have the Al hooked up with the SO3 to make the other double replacement reaction. If I had something like, oh God, magnesium chloride plus NaOH. Again, this one is not an acid-base reaction because I only have a base. This would be a double replacement, and I would make NaCl plus MgOH. And I'd have to put the parentheses around here. Put the parentheses around here in the 2. Okay. Are we good?
Can I just
Please, Jessica, ask.
thank you. I just want to make sure I understand. So do you always know it's going to be an acid because it has an H in front of it?
Unless it's water or hydrogen peroxide. Unless it's H2O or H2O2. Those are the only 2 substances I know of that begin with H that are not acids. Okay?
Okay. And then I'm just writing this down. And then you always know it's going to be a base because it has an OH at the end. Those are the 2 things that we look for.
Yes.
Okay.
Now, sometimes you're going to get something like this. When you have an acid with a carbonate, technically speaking, what happens with this is not really a base, is it, Jessica?
No.
What really happens with this is you get a double replacement, plus you get H2CO3. Okay? You get NaCl plus carbonic acid. But the carbonic acid has 2 very, very stable products. So the carbonic acid will not stay as carbonic acid. The carbonic acid will degrade down to CO2 and H2O. Does that make sense to you, Jessica?
Yes, thank you very much.
So technically, even though this does not have an OH in it, because of the overall reaction where you're making a salt and you're making water, technically speaking, this is an acid-base reaction. If I gave you this in a question and you answered acid-base, I would have to give you credit for it.
Oh, okay.
But the better answer, the more better answer is double replacement followed by decomposition.
Okay.
All right. Next reaction, combustion. The way you recognize combustion reactions is you have a hydrocarbon. Jessica, a hydrocarbon. What do you think hydrocarbons are made out of?
Hydrogen and carbon.
There we go. It has to have hydrogen and carbon with it. So the hydrocarbon can also have nitrogen, oxygen, other things, but it must have hydrogen and carbon. If you have a compound that has hydrogen and carbon in it, and your second reactant is oxygen, then you have a combustion reaction. The products will always be water and carbon dioxide. I don't want to go into the nitrogen thing. The product will always be water and carbon dioxide. So I need you to copy this down. This is a special balancing thing. When you have a combustion reaction, if only you have carbon and hydrogen involved, balance the carbons first, then balance the hydrogens. Then you got to look at the coefficient in front of water. If the coefficient in front of water is even, just balance the O's. If the coefficient in front of water is odd, double it. Then rebalance the H's, rebalance the C's, then balance the O's. Okay, we're going to go with this, and we're going to take away the coefficients.
Where can
All
I
right.
find this slideshow?
It should be up. It should be up in the thing. You didn't find it in the, you did not find this in the Canvas, in the My Courses? Kevin?
I'm currently looking for it.
Check the reactions thing. I'm not going to share this with you. Might as well stop share. Okay, course content.
I found it.
Then never mind. Okay. Share screen, reactions. Nope, that's not what I wanted. See, Kevin, you messed me all up now.
My bad. My bad.
You sound really horrified by that. Damn it. You didn't hear that, guys. There it is. Okay, so Jessica, your name popped up.
Okay.
I told you, balance the C's first. So what goes in front of the CO2?
3.
I have 6 C's over here. If I put a 3 in front of that, how many C's do I have?
Oh, you'll need 6.
6. Okay. Now, how many hydrogens do I have?
12.
What number goes in front of the H2O?
6.
Is the number in front of H2O even?
Even?
Is
Yeah.
it even? It's an even number. So if it's even, all you have to do is balance the O's. Jessica, I have how many O's from carbon dioxide?
12. I always
12?
get mixed up. I don't know what to do sometimes with the.
Okay, it's easy enough. This is easy enough, Jessica. Basically, what you do is you multiply the coefficient times the subscript. Okay? Does that seem fair to you, Jessica?
Like, can you just give me an example, I guess? I don't know.
Right here, this example. 6 CO2s. I have 6, the subscript for the carbon is 1, So 6 times 1, I have 6 carbon atoms. Okay?
Okay.
For the oxygen, I have 6. The subscript for the oxygen is 2. 6 times 2 is 12. I have 12 oxygen atoms. Now, you tell me, in 6 H2Os, how many oxygens are contributed by H2O?
6.
So I have 12 plus 6. How many total oxygens do I have on the right side there?
18.
So what number has to go in front of this O? This O2.
9.
Very good. Okay. Gabe.
Yes.
Gabe.
Yes.
Okay, Gabe. We have propane, the stuff that's in your gas grill, right? We have propane with O2.
Yes.
What products are made?
CO2 plus H2O.
Again, this is a gimme, guys. This is a gimme number of points on an exam. If I have a hydrogen and carbon compound and I have oxygen, the products are always going to be CO2 and H2O. Okay, Gabe, how many C's?
3.
What number goes in front of CO2?
A 3.
Okay, how many H's?
8.
What number goes in front of water?
4.
Okay, is the number even that's in front of water?
No.
No, 4 is not an even number.
Oh yeah, sorry. I thought you were talking about oxygen. No, yes.
No. You don't look at the oxygens. You
Yeah,
look
no,
at the
4 is
number
even.
in front of the oxygen, all right?
All right.
So how many total oxygens do I have on the left here?
10.
3 times 2 for 6 contributed by carbon dioxide. 4 times 1 times 4 for the waters. 6 plus 4 is 10. What number goes in front of here, Gabe?
5.
There we go. There we go. Okay, next one, Jasmina.
Hello.
Hi. I have benzene, C6H6 plus O2. What are my products?
Carbon dioxide and water.
Okay, Jasmina. How many carbons do I have?
6.
What number goes in front of the CO2?
6.
Okay. How many hydrogens do I have?
6.
What number goes in front of H2O?
3.
Uh-oh. That number's not even, is it, Jasmina?
Nope.
So what did I tell you to do? Do you remember?
Double it.
Double it. I'm going to make it 6. Next thing, you got to go back and you have to rebalance the hydrogens. I got 12 over here. What do I have to do to the benzene?
2.
2 in front of it.
Mhm.
Now you got to rebalance the carbons.
So 12 in front of it.
Now balance the oxygens. How many oxygens do I have from carbon dioxide?
24.
And the water?
6.
So I have 24 plus 6, I have 30. What number goes in
Yeah.
front of oxygen?
15.
Now, I challenge you. I challenge you to just by hand try and balance that equation and come up with 2, 15, 12, and 6. Now, the reason you're doing this doubling business, look at this side. Look at the left side of the equation. Okay? Is the left side ever going to be an odd number? I'm hearing crickets, guys. Look, whatever I put in front of the oxygen, is that ever going to give me an odd number of oxygen atoms?
No.
No. Okay, so whatever I put in front of the CO2, is that ever going to give me an odd number of oxygen atoms?
No.
So if I put an even number in front of water, is that ever going to give me an odd number of oxygen atoms?
No.
So if the number in front of the oxygen, I've got an even plus an even, that will never be odd. So as long as the coefficient in front of the water is even, then all I have to do is just go ahead and mess with the oxygens. However, if it's odd, then I have an even plus an odd number. I have an odd number on the right side, even number on the left. These would never be equal. Does that make sense to you? The easiest way to fix that is to double the number in front of the waters. So I make the oxygen atoms contributed by water to be even. Does that make sense to you guys?
Yes.
All right, Cassidy, what number? Let's do this quick. What number goes in front of carbon dioxide?
8.
In front of water?
9.
Is it even or odd?
Odd.
So what do I
double
do?
it.
What?
What? So it's 18.
Got to double it. Okay, now what number goes in front of this? In front of the CH18. I have how many hydrogens here, Cassidy?
18.
No, I don't.
Oh, sorry. My brain doesn't want to do that math right now. 36.
Thank you. So what number goes in front of the octane?
2.
2. Now I have 16 carbons. What does that change this to?
16.
Now all I got to do is figure out the hydrogens. I have 16 times 2. How many oxygens do I have?
32.
Plus 18 times 1.
50. So put 25.
For those of those that it's too early in the morning to do this math. 16 times 2 is 32. Plus 18 times 1, 18. 18 and 32 are 50. 25 goes in front of the oxygen. Are we good, guys? We good with combustions?
I had a question. So for the right side can never be odd numbers. It always has to be even.
The reason, Jessica, is because the oxygens are always going to be multiplied by 2 because the subscript on oxygen is 2. So the left side will always be an even number.
The left side will always be an even number?
Always has to be an even number because whatever you put in front of O2, you're multiplying it by 2, right?
Isn't 5 an odd number?
Yes, 5 is, but the total number of oxygen atoms is 5 times 2 or 10.
Okay, well, what about on the right side? I'm talking about the right side because every time there was an odd number, you changed it to an even number. So that's why I was asking, does the right side always have to have even numbers?
Yes.
Okay, and is that only for combustion or is that?
Well, wait. Let me, I'm sorry. First of all, Jessica, yes, this is only for combustion.
Okay.
And second of all, look here, this is balanced, but I've got an odd number of coefficients over here. But the number of oxygen atoms has to be even. So 3 times 2 is 6, plus 4 times 1 is 4. The total number of oxygen atoms is 10, which is an even number. Jessica,
Yes.
you're thinking too much about the explanation.
Well, because
Copy.
every time you had an odd number, you changed it to an even number. So I'm confused now.
The reason for that, Jessica, the reason for it is whatever you multiply, whatever you have in front of CO2 is going to give you an even number of oxygens because it's going to be multiplied by 2. Does that make sense to you?
I don't know. It's okay. I don't want to.
Jessica, if you're having trouble wrapping your head around the why, then just go with the formula here. Okay? balance the C's, balance the H's. Then you look at the coefficient in front of water. If the coefficient in front of water is even, just balance the oxygens. If the coefficient in front of water is odd, you have to double it. Then you rebalance the H's. Then you rebalance the C's. Finally, then you go ahead and balance the oxygens.
Okay.
Does that make sense, Jessica?
Maybe it will later.
Okay. If you want, stay after class and I'll try and explain why to you, okay?
Okay, thank you.
We have two more reactions to do. One is decomposition. Guys, with a few exceptions, I am not going to hold you responsible for determining the products, okay? Basically, all a decomposition reaction is you're taking a big molecule and you're making little ones out of it. So if I have a perchlorate or a perbromate, something like that, and I add heat to it, this molecule has the cation, it has a halogen and oxygen. If I add heat to it, I just make a simple salt, cation and anion, plus O2. So if I have a decomposition reaction, that means I'm taking a big thing and I'm making little things out of it. If I have a chlorate or a perchlorate, chlorate or a perchlorate. Let's do this. Now, we're going to just do chlorate or chlorates. If you have this and you apply heat to a chlorate or a chlorate, a chlorate is something like KClO3. If you have a chlorite, that's KClO2. The product is always going to be the chloride salt and oxygen. The chloride salt will always have the same subscript as the chlorite. And if the subscript is even, just balance the O's. If it's odd, balance the O's, then double it, then balance the metal and the chlorine. Some examples. If I have AlClO3 plus, taken 3 times, plus heat, all you're doing is you're taking the Al and putting it right next with the halogen. And you're taking this subscript and you get AlCl3. I have an O2 over here, okay? Now, I have 3 times 3, this is 9. I'm gonna have to double this. If I double this, I'm gonna have to double that. So, Jessica, you out there?
Yes.
All right, now it's gonna be complicated stuff. I have parentheses involved in counting the atoms. When you have parentheses involved, do the subscript outside the parentheses times the subscript in. I got 3 times 3. How many oxygens?
9.
Times the coefficient.
Yeah, 18.
So what number goes in front of the oxygen here?
9.
And I get, oops, excuse me, 2 of those. Okay?
Yes.
Bicarbonates and hydrocarbonates. They react with heat to make the carbonate, water, and CO2. So you recognize a bicarbonate by HCO3. That is the anion title for the anion HCO3. That is a bicarbonate or a hydrogen carbonate. When you heat this, what happens is you make the carbonate, you make water, and you make CO2. So immediately, if I'm doing this, I put the Na2CO3. That's one of my products because that is the carbonate. The other product is going to be water. The third product is going to be CO2. Now, since I have two sodiums, I'm going to put a 2 in front of the sodium, and this reaction is balanced out. If I've got magnesium bicarbonate and I heat that, I make the carbonate MgCO3 plus water plus CO2. Now, in this case, I got one magnesium. I got two hydrogens. I've got two carbons. What number goes in front of the MgCO3? What number
2.
goes in? Thank you. Okay. So I now have two magnesiums. What number has to go in front of this?
2.
Okay, so now I have, how many carbons do I have, Cassidy, on the left side?
12.
Nope. Carbons, not oxygens.
Oh, carbons. Sorry. You have 4.
4 carbons. Remember, my basic rule for balancing is balance everything except the H's and O's, then balance the H's, then balance the O's. I got two magnesiums. I have, whoa, I screwed up. That should be that. Because I have 2 carbons plus 2 carbons, and for 4 on the right side, I now have 2 times 2, 4 carbons on the left. So my magnesiums and my carbons are balanced. Next thing, go for the H's. How many H's do I have over here, Cassidy?
2.
No. 2 times 1 gives me 2 times 2. How many hydrogen?
4. 4. Sorry, I forgot about the coefficient.
So what has to go in front of H2O?
A 2.
2. So now I look at the oxygens. Left side. And I'm going to take this over here. Hopefully I'm trying to get this to look like that. Okay. I have how many oxygens, Cassidy?
12.
12. I have how many from the magnesium carbonate?
6.
6 plus how many from the water?
2.
6 plus 2 is 8 plus
8.
plus
Plus
2.
12. It's 12 total.
So 12 over here, 12 over here. This is now balanced, guys. So the 2 decompositions, I want you to know. Chlorates, chlorites. If you heat them, you make the salt you make the salt. If it's potassium chlorate, you would make potassium chloride plus oxygen. If you are taking bicarbonates and heating them, you make the carbonate plus water plus CO2. Last reaction, and this is going to be real simple. I don't know how to get it so you can predict these. So all I would want you to do with the synthesis is just recognize it as taking 2 simple molecules, combining them to make a bigger molecule. And what I mean by that is something like I take 2 H's plus an O2 and I make 2 waters from it. I take an N2 and 3 hydrogens, I make 2 NH3s because my product is a bigger molecule than either one of my initial compounds. I take magnesium, I react oxygen with it, I make magnesium oxide. Are we good, guys?
Yes.
Last thing, I'm going to mention this. I'm going to mention this so that you just know what it is, so that when you really get in depth with it next semester, you will have at least been introduced to the concept. When you have an oxidation reduction reaction, there are 2 processes that occur simultaneously. You can't gain electrons without losing electrons somewhere else. If one element loses electrons, that's called oxidation. If one element gains electrons, that is called reduction. One will not happen. The example that we've seen is the single replacement reaction. The neutral element is going to go from a 0 charge to a plus charge. The neutral element goes from neutrality to being a cation. It has lost electrons to go through that, so it is being oxidized. On the other hand, the cation that was part of the salt has now gained electrons, so it is now going from a plus charge to neutrality. It's gaining electrons, it is being reduced. Remember, if we have magnesium reacting with copper chloride, magnesium is more active, so the reaction goes, and I have magnesium chloride plus copper ion. The ionic equation is Mg plus Cu plus 2 2Cl minuses, yielding Mg plus 2 2Cl minuses and Cu neutral. Chlorines cancel out, so I have 2 half reactions. So I have my net ionic equation being Mg0 plus Cu plus 2, yielding Mg plus 2 plus 2Cl minus plus Cu neutral. I can break that. I'm sorry, go ahead.
Why is Mg 0?
Because I'm starting out with metal. Whenever, Kevin, whenever I have a metal just listed by itself, you know that to be a neutral entity.
Oh, okay, okay.
If I would put magnesium plus 2 up here, that would mean that I'm dealing with magnesium ion. Since there's no charge associated with this magnesium, you know that to be a neutral element. Now, if I would draw the net ionic, what is happening in the net ionic is I am making magnesium ion and I am making neutral copper metal. I can break this down into 2 half reactions. I can look at it like what's really happening to the magnesium. The magnesium is losing 2 electrons. So what that really means is that if I want to balance these 2 equations out, the magnesium is going to magnesium plus 2 plus it's generating 2 electrons. The electrons that it generates gets added to the copper plus 2 to make copper metal. Questions on that, guys? There's an easy way to remember what's oxidized and what's reduced. It's a mnemonic. You can remember Leo goes Gur. Loss of electrons is oxidation. Gain of electrons is reduction. Or you can use oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. I don't care which one you use. Basically, I stole both of them. And the other thing I want to emphasize, in an oxidation reaction, one process will not occur without the other. Okay, do you have any questions about reactions?
Guess not.
Okay, so we're going to stop share and we're going to go straight to the mole. We're going to go straight to the mole. Yeah, that's there. It's out. That's where it's up. Guys, I'm really not going to spend that much time. If you're having trouble with moles, if you can stay after class, then do it. I'm going to try and go through this real quick because for one thing, it's boring as snot. For another thing, you guys probably have this down already. All right. Topics we're going to go through. We're going to go through mole conversion. We're going to go through atomic weights, empirical formulas, and we'll probably get to percent composition on Thursday. So when we are dealing with this, when we're dealing with moles, we are dealing not with the fuzzy little blind creature. Stop. Why does this not want to do this? Thank you. Joke's ruined anyway, guys. We're not dealing with the fuzzy little small creature. We're not dealing with the ugly thing on your face. We are dealing with a counting number. Now, if I have a pile of marbles that weighs 394.38 grams and 10 marbles weigh 37.60 grams, how many marbles are in the pile, Gavin? What do I do?
Divide 394.8 by 37.6.
But that's 10 marbles.
And then multiply that by 10.
Okay. I can buy that. That would work. Okay. I decided to do it a different way, in which what I did was I divided the 37.60 grams by 10 marbles. So now I know that I have 3.76 grams for every one marble. If I divide the 394 by the 3.76, I'm going to get 105 marbles. Wait, I don't think that number's right. I think I've lost my marbles. Okay, the jokes don't get any better than that. More importantly, guys, what weighs more, a pound of gold or a pound of feathers?
They weigh the same.
Are you willing to bet your test grade on that, Cassidy?
Yes.
You don't want to do that. Whenever I give a question like that, you never want to do it.
Really?
Really?
What if I like to live life on the edge?
Then you're going to have the pound of feathers to fall on. So a pound of feathers does not weigh the same as a pound of gold because, ladies and gentlemen, gold is weighed in troy ounces. There are 12 ounces to a pound. Feathers are weighed in avoirdupois, which is 16 ounces to a pound. So in effect, feathers, a pound of feathers weighs more than a pound of gold. But that doesn't matter for us. What we want to know is basically what has more molecules in it, a pound of gold or a pound of lead? Anybody have an answer?
Maybe gold?
Okay, Kevin, you have your periodic chart with you somewhere.
No, I don't.
Okay. Somebody who has access to a periodic chart, tell me whether the atomic weight of gold or the atomic weight of lead is greater. Somebody's flapping something.
Lead is greater.
Lead is greater. So Jessica, per molecule of, or per atom of lead, this actually should be atoms. Per atom of lead, does it weigh more than gold does?
Per atom, no.
Per atom?
No.
You just said the atomic weight of lead was greater than gold. So if I have an atom of lead, does it weigh more than an atom of gold?
Oh, yes.
Okay. So that if I have my total weight and I'm dividing it by a larger number, I'm going to have a smaller overall number. By that, I mean, if I'm taking a pound, which is my overall weight, and I'm dividing my pound by 207, or I'm dividing it by 197, which number is going to give me a larger number? Dividing by 207 or dividing by 197?
197.
So gold is going to have more molecules than lead will. So if you have a given weight, there will be more molecules in that given weight of gold than there will be in lead. Do you all understand that? Are we good with that? We good, guys?
Yeah.
Okay. Gavin, if you owned a paper factory in St. Petersburg College, ordered 2.03, 2.02, 300,000,000,000,000,000,000,000,000,000,000,000 sheets of paper, would you sit there and count them all?
No, I have a machine for that.
Even if you had a machine, Gavin, you would be taking that entire machine and wasting that machine's time for forever and ever to count that many sheets of paper out. What would you do? How's paper sold, Gavin?
Usually by a package with containing a certain
Wait.
number of pages, varying. depending
Kind of
on
almost got the
brand.
idea, but Gavin, you're right. It's sold in a package. That package is called a ream, right?
Mhm.
So there are basically 500 sheets in a ream. And if you want to do it, generally speaking, there are 10 packets or 10 reams to every carton, right?
Okay.
So say you can put 100 cartons on a pallet, and each pallet contained 100, or each truck contained 120 pallets. If you did all that math out, you could determine how many pallets there were in a truck, and by reference, how many sheets of paper there are. Correct, Gavin?
Yes.
So you could basically, if you own that paper factory, just count the semis leaving your paper factory, and you will have delivered an accurate amount, correct?
That's assuming everyone put the right number of pages into the truck.
You have honest employees, Gavin. Nobody's out to steal money from St. Petersburg College.
Yeah, but they're not stealing from the college, they're stealing from the company.
So Gavin, isn't counting the semis a counting number?
Yes.
You use counting numbers all the time, guys. A dozen is how many? If you have a dozen waffle irons, Cassidy, how many waffle irons do you have?
12.
Okay, Jessica, if you have a ream of poodles, how many poodles do you have?
Is it 100? I'm not. Oh,
You don't-
500.
500. So they're just counting numbers. So the mole is the same thing. The mole is, I'll derive that in a second. Okay, guys, remember we said that when we're weighing out, when we're determining the atomic weights, we only use protons and neutrons. If we use 6 protons and 6 neutrons for our carbon-12, the total weight of our carbon atom would be this. Is that weight unwieldy to use? Somebody say yes.
Yes.
Thank you, Cassidy, for the cooperation. So if I say that my pile of carbon weighs 12 grams and an atom weighs this, and I'm saying 12 grams because I'm saying, okay, protons weigh the same as neutrons. So I'm basically going to say that I've got 6 plus 6 or 12 grams. I take that 12 grams and I divide it by what a carbon actually weighs. And amazingly enough, I get Avogadro's number. So this is basically how we determined what Avogadro's number is. And all Avogadro's number means is that that is equal to 1 mole. It is a counting number. Cassidy, If
Yes.
I had 1 mole's worth of golden retrievers, how many golden retrievers would I have?
6.022 times 10 to the 23rd.
That's exactly. We're lazy, guys. We don't want to sit there and count out the individual atoms when we are determining something like a chemical reaction. So what we do is we use a counting number. That counting number is called a mole. A mole is equal to 6.023 times 10 to the 23rd atoms. It can be referred to anything. So we have 3 relationships from this. 1 mole is equal to 6.022 times 10 to the 23rd atoms. 1 mole is equal to the atomic weight, and the atomic weight is equal to 6.022 times 10 to the 23rd atoms. Guys, ladies and gentlemen, after this, it becomes a dimensional analysis problem. You got to figure out what you want. You got to figure out what you're starting with. Then use one of these 3. Use one of these 3 relationships to determine what you need. If you're dealing with molecules, then 1 mole is equal to 6.022 times 10 to the 23rd molecules, which is equal to the molecular weight, which is equal to, this should be molecular weight. So guys, I'm going to emphasize the 2. If you're given a weight and you want to know moles, to get moles from weight, you're going to multiply it by 1 mole over the molecular weight. This is generally going to be in grams. The molecular weight is generally in grams. Grams cancels out, so you have moles. How many moles are in 23.495 grams of sodium chloride? You got to figure out what the weight of sodium chloride is. That is 22.9898 plus 35.453. I add those 2 up, I get 58.443 grams. That is the weight of 1 mole of sodium chloride. So I take the grams, I take that times 1 mole over the molecular weight, I end up with 4.0202 moles. Questions, guys? The other important one I want you to know is moles to weight. If you have the moles and you want the weight of it, it's the exact opposite of going from grams to moles. If you have the moles, you multiply it by the molecular weight over 1 mole. If you have 0.2348 moles of potassium bromide, what is the weight? The weight of potassium is 39.102. The weight of bromine is 79.904. I add those 2 together, I get 119.006. I have the moles, so I'm going to take the molecular weight over 1 mole and multiply it by the number of moles, and that will give me my weight of potassium bromide. Okay, guys, those are the 2 important ones. Those are the 2 ones that you have to be extremely facile. It shouldn't take you too long during a test to figure out how to go from moles to weight, or from how to go from weight to moles. The rest of this stuff is just a dimensional analysis problem. If you want to know atoms and you have moles, then you know the relationship between atoms and moles. It's 6.02 times 10 to the 23rd over 1 mole. If you want grams and you have molecules, grams goes on top, molecules goes on bottom. You have the molecular weight on top. You have 6.02 times 10 to the 23rd molecules on the bottom. You have your conversion. Now, 2 things, guys. Do I need to go into this in any further detail? You tell me.
I'm all right on it.
Guys, tell me, because it doesn't make any sense for me to just go over this when this is a dimensional analysis problem. If you're confused, speak up now or forever hold. Okay, I'm hearing crickets, so a couple things. If you're having problems with this, relook at the entire PowerPoint because I go through each one of the 6 types of problems individually. And if you're still having problems after that, go to the video or stay after class and ask me. There is one more conversion factor that you have to know, and that is at standard temperature and pressure. In other words, if the temperature is 0 degrees Celsius and the pressure is 1 atmosphere, there is a special relationship between the volume of a gas and 1 mole. In that case, 1 mole is equal to 22.414 liters of the gas. So how many liters of CO2 at SDP are there if you have 14.68 grams? Well, the first thing you have to do is you have the 14.60 grams, but you know there's a relationship between volume and moles. So the first thing you're going to have to do is you're going to have to take the grams and convert it into moles. You know that the molecular weight of CO2 is carbon 12 plus 2 times 16, 32 for a total molecular weight of 44 for the CO2. You take the grams, multiply it by 1 mole of carbon dioxide over 44.01 grams, you get the moles of CO2. Then, since it's an STP, you know the relationship between the volume and 1 mole. So you take the moles that you have, multiply it by 22.414 over 1 mole of carbon dioxide, and you get the volume. Okay, any questions?
I have a question.
I'm here.
You keep saying that we got to do this class next semester too. I'm confused by that.
Yeah, I don't. Kevin, do you have to take Chem too?
Oh no, I just have to take intro and chem, and then I gotta do
Then
all
don't
my
worry about it.
calculuses. Okay,
I
was
would say,
confused.
Kevin, probably about 90% of the people that take Chem 1 go on to Chem 2.
Oh, I'm just taking it so I can get into physics.
Then you go.
Okay.
Then you're done.
All right, cool.
Unless
Yeah,
you
the
want to
other
take an
10% are
elective.
engineering.
Unless you enjoy this so much, Kevin, that you want to take this as an elective.
That's gonna be a hard pass for me.
Does anybody have any other questions about moles, about the reactions we went over today? Because we're at the time right now.
Okie dokie. Have a good day.
Have a good day. I am a tad behind. I am a tad behind because I wanted to get through calculating molecular weights. That's not going to take any time. We'll get through that on Thursday, as well as empirical formulas. Any questions? Cassidy?
I am all good, honestly. This is like my favorite part of chemistry, so.
No, I was talking more along the lines. Weren't you asking the question? Was it you or Jessica that was asking the question on the combustions?
It was me.
Oh, yeah, I'm okay on that.
Okay, good, Cassie. Anybody else, before I deal with Jessica, anybody else have any other questions?
Thank you. No, I have no questions. Thank you.
Take care.
Have a good day.
You have a
Thank
good day
you.
too.
Bye-bye. Thank you.
Take care, Jasmina. Okay, let's stop share. Or I could do this. Now let's stop share. Okay, share screen. We're going to go back to here to figure out where I'm at. That's the mole. There we are. Okay, Jessica. You still there?
Yes.
Okay, wonderful. I'm gonna new slide. Okay. So give me a number of carbons.
5.
Okay. You have these two things together. What do they make, Jessica?
Is it acetate?
Nope.
Oh, I don't know. Just 8.
No, no. Remember, what did I say? You have a hydrocarbon. What's this at? Crap. I can't find my arrow. There it is. Okay. You have a carbon and hydrogen molecule, and you have oxygen. Do you remember what products you make?
CHO?
Nope.
I don't know.
That's fine. You make CO2 and water each and every time. Okay? You make CO2 and water. So just looking at your recognition, this is worth at least 2 points on the test. Your recognition factor, if you have a compound with carbon and hydrogen in it, and you have oxygen as the second compound, then your two products are going to be CO2 and water. Fair enough?
Okay, yes.
All right, now, going into balancing. If I put any number, pick a number.
5.
Okay, looking at the oxygens on the left side of this equation, is the number ever going to be anything but even?
No.
Because you have to multiply it by the subscript on the oxygen, which is a 2. So
Right.
any number times 2 is going to give you an even number on the left side of oxygens. Does that make sense to you, Jessica?
Yes. Uh-huh.
All right, now let's look at the right side. The right side's a little more complicated. Okay, if I put any number in front of CO2, is this going to give me let me do this. Why is that doing that?
Is this a combustion one?
Yes, this is a combustion.
Okay.
So because of that, because of the fact that you're multiplying the 2 subscript oxygen, this side is always going to be an even number of oxygens, right?
Yeah, I guess. Well, as long as there's a 2, right?
As long as the subscript on the oxygen is O2, then yes, you're going to have always an even number of oxygens on the left side. But look, the CO2 also has a subscript of 2. So whatever you have in front of the CO2, isn't that number always going to be even?
Yes.
Okay, so my first term, whatever number of oxygens got produced from the CO2, that's going to always give me an even number of oxygens, right, Jessica?
Yes.
All right, now, stop that. The number on my subscript for water is odd, right? Jessica?
I don't know what you're.
Okay.
I don't know what a subscript is.
You don't know what a subscript is?
No, it's
Okay.
like it's a lot of like new, like words that I just don't know, and I can't like just remember all of them. I
Okay.
can't. I'm sorry. I'm trying, but I just don't. I don't know what, I don't know. It doesn't mean an element. I'm not sure.
Nope. Okay, let me do this. Let me write it correctly. Okay. 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 Now, when you're looking at a chemical equation, or even if you're looking at a chemical that you're just looking at it and trying to identify it. When you're looking at the molecule itself, Jessica, the little numbers to the right of the element are what are known as subscripts. And that tells you how many of them are in the molecule. So if I'm looking at this number, this compound, C5H12, what that is telling me is that I have 5 carbons and 12 hydrogens. Does that make sense to you, Jessica?
Yes.
Okay, now, if I put a number in front of it, the big number in front of it is called the coefficient. And in order to determine the number of atoms total that are present, I have to multiply the coefficient times the subscript. Because what this is really telling me is I have 3 molecules of C5H12. Each molecule has 5 carbons. Okay, so I have 3 molecules times 5 C atoms per 1 molecule.
Is a molecule an element?
No, a molecule is the smallest unit of a compound.
Jesus Christ. I don't, okay.
Jessica, you're going to have to go back to the beginning. You're going to have to go back to like lesson 1. You're going to need to get this stuff down because you have to know what a compound is. You have to know what an element is. These definitions are in the PowerPoint that I labeled matter, M-A-T-T-E-R.
I've read all of this. I've done all the videos. I've studied all of this, but it's just so much at once that I can't remember every single word. Like it's impossible for me. I don't know, but I just can't remember every single word.
Okay, that's fair enough. Let's talk about where your background is. Did you take intro?
Yes.
You took intro, and your intro instructor didn't go through this stuff?
Yeah, but that was like 6 months ago. I mean, I've
Okay.
taken other classes since then, and it's just like I don't know if I really have like a memory problem or I don't know, maybe I'm not able to comprehend like everyone else. I'm not sure really. I can't remember certain things, and I think there's so much that I don't know. I just don't get it.
I'll tell you what I'm going to do I'm going to stop right now, okay? And I'm going to